In this video, we're going to look at logarithmic equations. And for these, we're going to look at similar methods that we talked about for the exponential equations, except for now we're looking at equations that have logarithms in them. For logarithmic equations, we're going to look at three types. And again, they're very similar to what we did with the exponents. So the first is the type where all terms have logarithms in them. So we can simplify it down to something that looks like a log of A equaling a log of B. And again, very similarly to what we did with the exponentials, is if we have this type of equation, we can basically drop the logarithms and just look at equating the arguments. And so it makes it very nice to solve. We're usually going to be looking just at the equation, a linear, a quadratic, or something else. Okay. The second type is if there's at least one term without a logarithm. Okay? And so when we simplify it down, it's going to look something like log of A equaling B. And so here, the key is we're going to use our equivalence to solve. And so whatever our base is, I kind of forgot to write a base in here, so let me put base C, just for the sake of writing what this is going to look like. In this case, if I have log base C of A equaling B, so I simplify it down to a single logarithm, then C to the B will equal A. And so we're back to an exponential equation, which we know how to solve these now. Okay? And then the other types are just like what we saw with the exponentials. We could have logarithms that are in the form of quadratics, powers of logs, logs of logs. All of those types of things would fall under the other category. And again, it just means that we have to use something else in order to get it back in terms of one of these two, instead of just combining our logarithm properties. Okay. So our first couple of examples, we're going to be looking at the ones in which all of the terms have logarithms. Okay. And all of these are going to look fairly similar. We're going to use our basic properties of logarithms to combine them down so that they look like a log equaling a log, and then we solve. So in this first example, log of x plus log of x minus 1 equaling log of 4x. Again, every single term has a logarithm. So the first thing we're going to do is simplify it down so I just have a single logarithm on the one side. And so here, because of the addition, this means I'm going to multiply my logarithms. So I'm going to have an x squared minus x equaling the log of 4x. Okay. Now that I have the logs equaling each other, I can just equate the arguments. So x squared minus x has to equal 4x, and now it's back to just a quadratic that I can solve. So I'm going to move all the x's to one side. Here we can factor. So x will equal 0 or x will equal 5. Okay. Now, with your logarithms, unlike your exponentials, I am not done at this point. Okay? Exponentials, the nice thing about them is that your domain for an exponential is all real numbers. For a logarithm, our domain is restricted. So our x's have to be greater than 0. And I'm actually going to go back and say that again. Not just the x's, but the argument has to be greater than 0. Okay? So if I'm looking at my logarithms here, every value that I plug in for x needs to make these arguments positive. And so here I can see if I plug in 0, well, it's problematic there, but even more so it's problematic there because I'm going to get a negative argument. So here I know x equals 0 cannot be a solution because it's not going to make sense in our logarithm. For 5, if I look, well, plugging 5 into each of these, I'm still getting a positive value. And again, the only way I'm really going to be able to check that is to plug it in and get the decimal approximations for these. But here, because it's a positive argument for all of them, this would be my solution. Okay? Alright, so let's look at the next example. So same thing, I'm looking at all terms having logs. In this case, they're all natural logs. So ln of x minus ln of x plus 1 equaling ln of 3x. So again, first thing I want to do is combine my logarithms so I have a single log term on each side. So here, because of the subtraction, I'm going to divide my arguments. Okay. From there, again, the natural log equaling the natural log says that my arguments have to be equal. And so in this case, I'm now looking at a rational equation to solve, which again we've done before. So these, I'm going to get my LCD, which happens to be x plus 1. I'll multiply through, so x will equal 3x times x plus 1. I'm going to go ahead and solve by distributing and then moving all the x's to one side. Okay. Now I can factor. So we see that x will equal 0 or x will equal negative 2/3. Okay. Again, same thing. I'm not done at this point. I still need to go back and make sure that all of my arguments are strictly greater than 0. So here, if I plug in x equals 0, well, that first one becomes a problem because it's not defined at 0. And if I look at the negatives, well, the negatives make a couple of them problematic. Okay, so in this case, this tells me that there is actually no solution for this logarithmic equation. Okay, so again, be careful with these because just because I'm getting values does not mean they actually work. You have to go back and double check and make sure they actually make sense in the problem, meaning that they're in the domain of the problem. In this next set of examples, we're going to look at logarithmic equations where at least one term does not have a log in it. Okay, and we're going to start out with kind of the nicer ones, and then we'll look at one that's a little bit more involved. So this first example, ln of x equals 10, would be our first example. And again, remember here, if we can get it to be a log equaling a number, then we want to use the equivalence to solve, meaning we're going to turn it into an exponential equation, and then you solve the exponential. So in this case, ln of x equaling 10, well, to turn this into an exponential, remember this is base e, so this says that e to the 10th is equal to x. Okay? In this case, that's it. There's our solution. E to the 10th is a number. In this case, because it's a larger power, we don't want to multiply that out. It's going to be huge, on the order of 10 place values. So here we can just leave it as e to the 10th equals x. Okay. In this next example, a little bit more involved, but the same idea. So I've got a logarithm equaling a number. So again, the first thing I'm going to do is I'm going to look at the base and then change it to an exponential. In this case, it's a common log, so we can think base 10. So we're going to take 10 to the second power equaling the 3x plus 5. Okay? This one is something a little bit more doable. So 10 to the second is just 100. Now we're just looking at a linear equation that we need to solve. So we'll subtract the 5. Go ahead and divide out by 3. Okay. And again, in both cases, you should check and make sure that your value makes your argument positive. In this case, and in the last, it does. So that's it. There's our solution. Okay. This last example is the one that I said is going to get a little bit more involved. It's still the same type of problem, but it just has a couple extra steps. And so here we can see log base 2 of x plus 1 minus 12 equaling log base 2 of 2x minus 3. Okay. Again, the first thing we notice is that there's a term in here that doesn't have a logarithm. So I want to start by isolating that term. I want to get all the logs to one side and get that 12 to the other side. So we're going to say log base 2 of x plus 1. We're going to move this other logarithm over. So log base 2 of 2x minus 3. And we're going to move the 12 to the other side. Okay. And again, that just isolates that constant term so that we can do just like we did in the last two examples and simplify. Again, because I have more than one logarithm, I need to combine these. So because of the subtraction, this is going to be log base 2 of x plus 1 divided by 2x minus 3 equaling 12. Okay. From there, we now have a log equaling a number, so we can change it to an exponential. So the base to the answer, so 2 to the 12, will equal our argument, x plus 1 over 2x minus 3. 2 to the 12th, huge number. We'll leave it as 2 to the 12th for now, but we can still solve. So I need to look at my LCD since I have a rational equation. LCD in this case is the 2x minus 3. I'm going to multiply both sides by that. So 2 to the 12th, 2x minus 3, equaling the x plus 1. Again, to get the x's on the same side of the equation, I'm going to need to distribute. Okay. Notice when I multiply here, both have base 2, so 2 times 2 to the 12th is 2 to the 13th times x minus 3 times 2 to the 12th equals x plus 1. Okay. And go ahead and get my x's to one side and everything else to the other side. Okay. Here I can factor out an x. And then divide out. Okay. Now again, simplifying this, you have to be very careful if you're going to. This right here, if this was an exam problem, would be full credit. You don't have to take that any further. If you are asked, for example, in WebAssign to get a decimal approximation, remember that multiplying 3 and 2 doesn't work because that 2 is raised to a power. So you would have to do 2 to the 12th first, then multiply by the 3, then add the 1. Same thing on the bottom, 2 to the 13th minus the 1, and then get your number. As far as homework and the exam go, if it doesn't ask for a decimal, leave it there. Okay. So as you can see, it's very similar to the other ones. The only difference, again, is a couple extra steps because you have to combine it down to a single logarithm first and then solve that remaining equation. So the last set of logarithmic equations we're going to look at are the other types, where these include where we have logs of logs, powers of logs, or things like what we saw with the exponential, where maybe there's logarithms within a quadratic or within a rational equation. This first type is where we have a log of a logarithm. And it doesn't quite fall into the previous examples, but it does also. It's very similar in that I can think of it as a log equaling a number, even though there's a log embedded in the log. Okay? So we have a composition of logarithm functions equaling a number. And this is going to start very similar to our all terms but one have a logarithm. I can think of taking this as an argument and just kind of ignoring it for a moment and look at log base 2 of that argument equaling 4. The log base 3 of x will just get moved on as the argument. So here, I can start by rewriting this as an exponential. So my base of 2 raised to the answer, which is 4, will equal my argument, log base 3 of x. I can simplify a little bit, so 2 to the 4th is just 16. And then I am back to just all terms but one equaling having a log. So here I'm back to just a basic logarithmic equation where I can use my equivalents to rewrite. So my base of 3 raised to the 16th will equal x. Again, the larger power, I'm just going to leave it there. And again, we can notice that 3 to the 16th is definitely going to be a positive value in my logarithm. And the log of that is also going to be positive because 3 to the 16th is bigger than 3. So this answer makes sense in my problem. It is within the domain of the function. Okay. For the second one here, let's look at log of x to the 16th equaling log of x squared. Now, reading that like I just did, you have to be careful because your powers do mean different things here. So if you remember, we had a property that says if I have an exponent on the argument, I can move it down to the front. And I said you had to be careful where the parentheses were, because if that exponent is on the logarithm, I can't move it down to the front. Okay? So here, if I'm looking at this, the 16th is on my argument, so I can actually rewrite this as 16 log of x equaling log x quantity squared. Okay? Well, looking at that, it doesn't really help me in solving, at least not at first glance. But if I think of this a lot like our quadratics, I can solve this fairly easily. Okay? I'm going to rewrite it a little more so that maybe it's a little easier to see. Okay? So now I have a logarithm that's squared and a logarithm to the first power, so I can actually factor out a log of x. And then what's left over is a log of x minus 16. Okay? So you got to be careful with those exponents. The ones outside of the logarithm, we can't move that power down, but it does work just like a regular exponent should. It means I'm looking at multiples of that value. Now to solve, well, I'm looking at my zero property. So log of x will equal 0, or log of x will equal 16. Okay? Here, these go back to our log equaling a number. So base here is 10. 10 to the 0 will equal x. 10 to the 0 is just 1. Or over here, 10 to the 16th will equal x. Again, large exponent, we'll go ahead and leave it in the exponential form. Both of these, if we plug them back into our originals, will give us positive arguments, so both solutions work. And you can check it further again by plugging in the decimals. Okay? All right. And then for our last one, 4x squared, natural log of 2x, minus 6x natural log of 2x equals 4 natural log of 2x. Now, a lot of people, when they first look at this problem, they want to do what seems obvious, and that is, there's a natural log of 2x in every term, I'm just going to cancel those out. Don't do that. The problem with doing that is you lose some of the solutions here. So it's good to notice that that natural log of 2x is in every term, but instead of canceling them out, what we're going to do is we're going to rewrite, move everything to one side, and factor it out. Okay, so we'll pull a natural log of 2x out. And then we can see what's left over is just quadratic. So we can factor this as well. So it'll be minus 8 plus 2 to give us the minus 6. So there would be our factored form of our equation. Okay? And again, the reason I don't want to just eliminate the ln of 2x is because now I can see in the zero product, I need to solve for that part of the equation. These last two are just linear, so we can see x will equal 2 from this last one. Here, moving the 2 over and dividing out by 4, we'll get a negative 1/2. Over here, we're back to our logarithm equaling a number. So our base here is e to the 0 will equal 2x. E to the 0 is just 1. So x will equal 1/2. Again, just like all of the other logarithmic equations, we're not quite done. We need to go back and make sure we get positive arguments for these. So if I plug in 1/2, my arguments just become 1. That's okay. At negative 1/2, they become negative 1. That's not okay. And then at 2, they all become 4, which is okay. So here, our solutions are x equals 1/2 and x equals 2. Okay. Again, just like your exponential equations, many of your logarithmic equations will be of these other types. And so, again, it's just recognizing where I can move my logarithms around or how to rewrite the equations so that I can actually solve for those logarithms. And many of these problems, like these, you will have to go back to prior equation methods. So looking at quadratics, rationals, radicals, things like that, and being able to simplify down or factor or move things around so that you can solve. Lastly, don't forget, for logarithmic equations, you have to check your solutions. Those domains are 0 to infinity, so you need to make sure that your arguments are positive with whatever values you're getting for your x's, and then exclude the ones that don't work.